Hello, welcome back. Let's continue analyzing BJT circuits in DC and actually doing some design and focusing on some useful circuits. So in the previous video, we went over how to design a current source using a single BJT. This is intended for discrete transistor. And if you recall, I mentioned set the voltage at the meter low, like at 1 volt. Once you do that, you can select the value for RE. So 1 volt over 1K will give you the 1 milli. That is our objective here. In order to do this, what we need is to set the base, have a supply at the base that is 0.7 volts approximately, higher than the meter. So let's set the base at 1.7 volts. Now the 1 volt over the 1K gives us the 1 milli in the emitter. Our model was that if we have the base emitter at 0.6 to 0.7, what we have here, between the base and the emitter, a junction, then we have current in the collector, as well as in the emitter, and that the collector current is approximately equal to the emitter current. And so we were able to design that 1 milliamp. We saw that this was a stiff current source, certainly worked for a load of 2K, but as you kept increasing it, you got to a point where the transistor stopped working in the saturation region, which requires the voltage in the collector to be higher than the voltage of the emitter by around 0.2 volts, as well as in the voltage at the base. And so around 8.5K, it starts going down. Now, what happens if we were to, instead of designing so that the voltage at the emitter was 1 volt, we put it, for instance, at 5 volts. Let's imagine that our design was something like this. So we have our load here. And we said, well, let's set this at 5 volts. And we will have a supply at the base of 5.7 volts. Therefore, we have our base emitter junction forward bias, which is required for the active region, 0.7 volts. With 5 volts, if we want a 1 milliamp emitter current, we set RE in this case to 5K. And we have 10 volts here. Now, because our collector current is approximately equal to our emitter current, this is our load current, we will get the 1 milliamp that we want for our load. Okay? What's the problem with this circuit compared to the previous one? Is this better or worse? Well, what we see is that it's going to have less compliance. Remember, the collector voltage in this case, as in the previous circuit, is going to be VCC minus IC times RC, or VCC in this case minus I load times R load. And it needs to be greater than the emitter voltage plus 0.2 or so. And so now the emitter is higher than before. And so what we expect in this circuit is that instead of going all the way like before to 8.5K RL, I load 1 milliamp, is that it's going to decrease, right? So you can see that if we have a load of 5K, as an example, times 1 milliamp, that's a voltage drop of 5 volts. And so that will put the collector voltage already where the emitter is. So this is going to be less than 5K. 5K certainly will be the maximum. Let's see if that's the case. Let's analyze this circuit. Let's do a parameter sweep. Actually, before doing that, we'll see that this also will work for a 2K. That was the design objective. So this is valid. Let's go ahead and look at the voltage levels first. 10 volts, 1.7 volts, 5.7 volts at the base. At the emitter, it's going to be 0.7 less, so it's going to be close to 5. And so our voltages are right. If our source is at 10 volts, and we have a 1 milli drop through a 2K, at the collector, we are going to have something like 8, right? Boom. So everything works in terms of the voltage levels. Let's look at the current to make sure that we are providing the 1 milli, which was the design specification for this discrete transistor circuit. We got it. So the circuit is working as intended. You remember the model that we are using is very simple. Voltage base emitter between 0.6 to 0.7. Okay. For very low current, it's going to be closer to 0.6. For a high current, 0.7. If you're using 0.7, you're going to perhaps overestimate a little bit, very slightly. And IC is approximately equal to IE. When that happens, as long as you have the collector emitter voltage greater than 0.2 volts. Okay, so let's look at the load. We predicted that this was an inferior circuit because we are losing compliance, right? Instead of 8.5K, we're going to be less than 5K. To look at that, we create a variable, rload, and then we do a parameter sweep. So with the spice directive, that stem param rload 0.5K to 10K increments of 0.25K. So we are starting at 500 ohms to 10K in increments of 0.25K. Let's do it. As expected. So what you can see here is that we reduce the compliance. So compare it with the circuit before, the 1.7. Look at this circuit. Simply because the emitter voltage was lower. So we have seen at a single supply, or actually this requires two supplies, source, we have used the basic model for the transistor in DC, are getting familiar with finding terminal voltages, etc. And we are using some useful circuits to understand these concepts, meaning current sources. Now let's create a little bit of a better current source. This one, you realize you need to have at least two supplies. You need to have the VCC here, and then you need to have another one to set to the base. Can we design it all with a single supply? That's the topic of the next video. Thank you.